Kia ora team and welcome to another online tutorial. Today we're going to be talking about calculating acceleration, as well as, similar to our last video, rearranging our equation, but this time we're going to be finding change in velocity or change in time, seeing as those are the things in our equation. I would like to start by defining acceleration, okay? Well, we've said that acceleration is the rate at which velocity is increasing, all right? We have our equation for acceleration, A equals delta V over delta T, with A, or acceleration, being measured in meters per second squared, and we can write that again as ms negative 2, okay? This triangle, which you may not have seen before, being delta, which means a change in, okay? V being velocity, which we know is measured in meters per second, which we write as ms negative 1, and T, time, measured in seconds as always. Let's get into an example. I'm going to go through two with you and then do a little bit of a rearranging. For our examples 1 and 2, we're going to look at a car speeding up and a car slowing down, accelerating or decelerating respectively. We are going to get rid of the kilometers an hour units, right? And we are going to deal with meters a second for all ours, just to make it nice and easy for us, so we don't have to do any additional calculation. 10 seconds is our time, okay? We've got a car that is accelerated from 30 meters a second to 60 meters a second in 10 seconds, okay? And for our second example, a car that has decelerated from 60 meters a second to 0 meters a second, and we're going to calculate their acceleration and deceleration respectively. So for one, okay, I'm going to always write down my equation first, delta V over delta T. Okay, I'm going to look at the information that I've got and I'm going to substitute. Okay, so I'm going to put in my delta V, which is 30 to 60, which will be 30 meters a second, over the time, 10 meters a second, and I'm going to get 3. Now my answer here is not good enough because I need to give it a unit, which is going to be 3 meters a second per second, or meters per second squared, okay, or ms negative 2. For our second example, we have deceleration. We're going to use the same calculation, but when our change in velocity is looked at, it will be negative. So we've gone from 60 meters a second to 0, okay? So when we write our equation, as we always start off with, we're going to say delta V over delta T. Our change in velocity is going to be negative 60 over our change in time, which is again 10 seconds, and we will get negative 6 meters a second per second. All right, meaning that, and when we deal with meters a second per second, it's saying that every second we are slowing down an additional 6 meters a second. Okay, so if we start off, we have a velocity of 60 meters a second later we have 54 meters a second after that we have 48 meters a second, etc., until we get to our 0. And if you do that 10 times using our deceleration, you'll get that change. Okay, let's look again at quickly rearranging our equations or formula to find change in velocity and change in time specifically. So if we're looking for change in velocity, we're going to write out our equation A equals delta V over delta T. Remembering that when we're dealing with an equation, if we do something to one side, we have to do it to both. Okay, I can see that I want to make my V the subject of the equation, so I want to get rid of T on this side. So I'm going to change both sides by timesing it by delta T, okay, which will give me A times delta T equals my change in velocity, okay, which should make sense, seeing as how fast we're speeding up times how long we're speeding up for is how much we've sped up. If we were to rearrange for our change in time, okay, if we're looking for delta T, we'd start off the same as we always do with writing out our equation, delta V over delta T, okay. There's going to be an additional step here or two. All right, we want to make T the subject of our equation. We can see that it's under V. That doesn't really work. So we're going to times again both sides by delta T to get it out from underneath delta V. Okay. which will give us a times delta t equals delta v. All right. Now, remembering that we want delta t as the subject of our equation, so we're going to get rid of our acceleration by dividing both sides by a, okay, which would cancel our a on the left-hand side, and we get delta t equals delta v over a. Now, again, this makes sense, saying how much we've sped up divided by how fast we're speeding up will tell us how long it takes for us to speed up. If we plug in the numbers from our example into our equations, we can see that they match up. We can say our acceleration, 3 meters a second times 10 will give us our change in velocity, which is 30, which we can see here. Okay. For our change in time, we can say, all right, cool, it's going to equal our change in velocity over our acceleration, our 30 meters a second, divided by 3 meters a second, and it'll give us 10. So it matches up. A reminder that if you're struggling to deal with rearranging equations, you can use our magic triangle. Remembering that you cover what you're looking for. Acceleration equals v over t. All right. Change of velocity equals acceleration times change in time. And change in time, or time taken, equals change of velocity divided by acceleration. Okay. So team, hopefully that's helped you see how we can calculate acceleration, what acceleration is, why it has the units that it does, what these symbols mean, okay, and how to use, again, the equation, as well as rearranging for change in velocity or change in time. Hopefully this helps you get out there and get into some level 1 mechanics team. Good luck.